So to determine the rate law for reaction, we have to do this experimentally. And so I'm going to walk through the method of initial rates, which is a way of seeing how the concentrations of reactants affect the initial rates of the reaction. And that allows us to determine what the order is with respect to that reactant. And that'll allow us to build our rate law. But we really need to see like what is the dependence of the rate on any specific concentration. And we do that by varying the concentration and seeing like, well, what's the effect on the rate? So let's look at again our really simple case where we just have one reactant A and it's forming some set of products. And we're focusing on the reactants, so we don't even care what those products are. So the initial rate of our reaction is that average rate between the time zero and our first data point that we take. So it's going to be our first constant or our concentration at time one minus our concentration initially, all divided by the change in time. So this A with the zero at the end, this is our initial concentration. And this is at time one. And we're using this negative here because we're looking at reactants. So if our order for this reaction, our dependence on the concentration of A is, let's say, zero, then we can see a change in concentration and we can look at and we won't see a change in the initial rate. But if our order is one, then if we double our concentration initially of A, we should see the rate of the reaction initially be twice as much too. If that rate order is actually 2 with respect to A, then if we double the amount of A that we start with, so we double its concentration, we should expect to see the rate quadruple. We'll see a larger dependence on it. So we're going to change the concentration we start with and see what's the effect on the initial rate. And that'll allow us to understand what the order is. Let's walk through an example because I think that's the easiest way to see this. All right. So here's a bunch of stuff on the page. So let's say I'm going to do an experiment. I'm going to set it up. So I'm going to do everything the same, except I'm going to change the concentration of my reactants, just one of them at a time. Remember, it's an experiment. So just change one variable. So I have a reaction right here where I've got 3A plus 2B is going to form products. So my rate law is going to look like rate time is equal to my equilibrium, or sorry, times my rate constant times the concentration of A to the order M, which I don't know what it is yet, times the concentration of B to the order N, because I don't know what it is yet. So it's just a variable. So my goal is to figure out what these pieces of information are. I need to figure out what K is, and I need to figure out what M and N are. So we're going to focus on the orders first. So to do this, I'd go into the lab and I would measure the initial rate of the reaction for a given set of concentrations, and I would change them. So I have 3 experiments that I did, or 3 trials, and between trial 1 and trial 2, I'm changing the concentration of A, and I'm keeping B the same. And then when I move on to experiment 3, I'm going to then change the concentration of B. So here I'm changing the concentration of B from point 1 to point 2 between experiments 2 and 3, and I'm keeping the concentration of A the same. So between these 3 trials, I can do a comparison of a change in A, and I can do a comparison in a change of B. And then I measure the rates, the initial rates, by just taking the concentration at a specific time after interval afterwards and calculating that average initial rate. And so I get then the rates for each of these reactions. So the way I'll find the order with respect to A is by comparing experiments 1 and 2. And so by comparing experiments 1 and 2, I can see what happens when I change A specifically. So in this one, I'm doubling A, and if I look at the rate, just like looking at it, I can see that it's quadrupling or close to it. It's increasing. So I automatically know that my order is not 0. So to figure out what that order is, I'm just going to try to get the ratio of them. So in this case, what I'm going to do is I'm going to just divide my rate law by my rate law for the 2 experiments. So I'll have rate 1 is going to correspond to experiment 1. and rate 2 will correspond to experiment 2. And so I have those rates right here. I just pull them from my table. And so that ratio of the rates is going to be equal to 4. So that 4, I now am going to set equal to my rate laws. So my rate laws for each of these are the same, but I can now populate information that I have from my table, which is information about concentration. So I have them set up here. So I have my rate law for experiment 1 and experiment 2 over one another. And some of the things between these are the same, like K. So K will be the same. So we cancel it out. And I'm noticing that the concentration of B is the same. So I can cancel that out. That also cancels out the N. And so I end up with 4, which is the ratio of my rates, is equal to, let's do it like this, the concentration of A divided by the concentration of A all to the exponent of M. And the idea here is to solve for M. So I end up with 4 is equal to 2 to the exponent M. If I take the log of both sides, which I'm doing right here, I can make that exponent something that I can deal with algebraically. It comes out in front. So that 2 to the M becomes M log 2. Sorry, right there is equal to log 4. So then M is really then equal to log 4 divided by log 2, which is equal to 2. So that tells me that my exponent is 2. That means my order is 2 with respect to A. And that's how I'd write it out. I'd write like the order is second order with respect to, and I'm abbreviating that, sorry, with respect to the concentration of A. All right, so that's one piece of my rate law. So now I can say, all right, well, I know that rate is equal to my rate constant times the concentration of A squared times the concentration of B to some exponent I don't know yet. So I've got one piece. Now to go get the second piece. So next I'm going to try to go find that order for B. So here's how we find the order for B. So it's the same thing, except now we're going to be comparing experiments 2 and 3 because this is where we see our change in B. And A will stay the same. And we look at our rates that we calculate from our experimental data, and these are the initial rates, and we see that they're the same. So without doing any math, if the rate stays the same when I change the concentration, it has to be zero order. And so you don't need to like go through a big mathematical proof of that if you don't want to. You just be like, it doesn't change, it's zero. But I'll show you how to do it if you aren't sure. So in this case, I'm doubling B. I'm not seeing a change. So I'm going to essentially put, again, my rate laws over one another. So I have the rate of experiment 3, my rate law for experiment 3 right here, and my rate law for experiment 2 right here. And some of these things are the same, and some of these things I have information for. So I can plug in information for my rates, because those are coming from right here, my 4.8 times 10 to the negative fourth for both. My K's cancel because they're the same, and my A's cancel because they're the same. So I get a value that's just the ratio of the rates is going to be equal to the change in concentration of B to the N power. And so these rates are the same. So when I plug those in, I get a value of 1. So that's right here. So I get 1, just to simplify this, 1 is equal to this concentration of 0.2 over 0.1 to the N power. So that's going to be equal to 2 to the N because the 0.2 divided by 0.1 is 2. And so now I have something that I can solve, and 2 to the N equals 1. If I take the log of both sides, I can solve for N, where N is going to be equal to the log of 1 divided by the log of 2, which is equal to 0. So I have a 0 order dependence of B, or on the concentration of B. All right, cool. So now in my rate law, I've got more information. I know that rate is equal to my rate constant times the concentration of A squared times the concentration of B to the 0 power. So now I know the order for both A and B. Now I just have to figure out K next. And when you write these, you can write out the order with the 0 exponent, but anything to the 0 power will equal 1. So you can rewrite this as just K to the concentration of A to the second power, and it means the exact same thing. All right, so the last step here is figuring out what the rate constant is. Now, the rate constant is unique to every reaction. So this will be unique. And so the way I solve it is just algebraically. I just choose one experiment, and I can choose any one, or trial, whatever we're calling them. And I'm going to plug in the information that I have into my rate law and solve for K. So here I know that, let's do this kind of in between. So I know for if going with my rate, if I'm going with the first experiment, I know that, so I'm going to look at experiment 1, that my rate is equal to 1.2 times 10 to the negative 4th. Is that going to show up? My rate is equal to 1.2 times 10 to the negative 4th. There it goes. And that's equal to my concentration of A, which is 0.1 squared, and K's in there too. So now I just solve for K, which is what I'm doing right here in this line. And so when I solve for that, I'm going to divide my rate by the concentration of A squared. That's going to give me K, which is going to give me a value of 1.2 times 10 to the negative 2. So that's my K value. Sorry, this is jumping all over the place. And so now I can write my full rate law. My rate law is going to be keep the concentration a variable, because I'm going to be able to change that. And the rate's going to be dependent on it, so it stays a variable. But the rate constant will not change when I change my concentration, so that stays the same. And the order of my reaction doesn't change when I change the concentration, so that remains the same. So my overall rate law is this. Its rate is equal to 1.2 times 10 to the negative 2. Inverse molarity seconds times A, the concentration of A to the power of 2. And so your rate law is always going to need to have a numeric value for K and for the orders for it to be a rate law. The other thing that's important is the units of K. The units need to match the overall order. So the overall order for this reaction is 2. And that's just the sum of my exponents, right? So it's really 2 plus 0 is equal to 2. So I have an overall rate order. Now my units need to be, of K, are going to be dependent on the overall order. So that way my calculation always works out to give me units for rate, which is going to be molarity per second, or moles per liter times second. And so here is a handy chart. So you can figure it out just algebraically using the different units and figure out what you would need to be able to cancel out with the units you'd be getting from your concentration to the order. But here's kind of the shortcut. So if you have an overall order of 0, 1, 2, 3, or 4, here are the units that you need to have for K right here. And so these are all in liters and moles rather than molarity. So if you wanted to do these versus like where moles per liter equals molarity, whoops, we can do that. So remember that molarity equals moles per liter. And so for an overall order of 0, we have molarity per second, right? That's our rate units that we expect to have. We have 1 over seconds for first order. We have inverse molarity seconds, so 1 over molarity times seconds for second order. And then we have 1 over molarity squared seconds for our second order, and 1 over molarity cubed seconds for our third order. You can use either version of these. It's the same units. It means the same thing.